Now we are going to start with an interesting topic, that is the activation energy. See, you know that what is chemical reaction actually? You know that in a chemical reaction what we get to see that reactants get converted into products. Right, this is what happens, that like you can have one or more reactant, like the number of reactant can be any, number of product formed can be any, but what is the basic thing about the chemical reaction? Obviously the reactants are going to change into products. They cannot change as such, right, because they have some kind of bonds present prior in them, right. So we need to break those bonds and we need to form new bonds, then only it will give rise to product. So that means, coming to the point, that when a reaction happen, what you get to see in all kind of reaction, whether it is a combination, displacement or whatever kind of chemical reaction, what you get to see? We get to see that the reaction involves breaking of bond, right, I'll write here, breaking of bond and forming of new bonds. This is what happens in the reaction. Now these bonds do not break themselves, you can say they do not break own self. We need to supply certain kind of energy. So that means this breaking of bond need energy. Right, so that means if when a chemical reaction occur, there are you can say the first thing is that their prior bonds will break and the new ones will be formed, right. So that means for breaking of bond, they will not occur themselves, like the breakage will not take place itself. We need to supply it with certain amount of energy, then only the breakage is going to take place. That means their prior bonds are going to break only if you supply it with certain amount of energy, or you can say they need certain amount of energy to just break their bond, whether you supply it from outside, whether this energy is present in themselves, right. So we are not concerned with that we are supplying it energy from outside or the energy is present in themselves, like before, there is an extra kind of energy which is present in them. Our concern is that the breaking of bond needs the energy. Right. So now this energy will come from which place, we are not concerned with that, but at this moment we are just talking about that if we need to break the bonds, obviously the energy is needed, right. So when the bonds are broken, that means the energy is required for that breakage, and then when the formation of new bond is there, it leads to the release of energy, right. So formation of bond, release of energy, breaking of bond needs energy, right. Now our concern is first, like for the chemical reaction to happen, the first step is to break the bonds, right. So that means first concern is that we need to break the bonds. That means the energy is required for breaking that bonds. Now you can say that how the bonds are going to break now. See, for breaking of the bonds, or when we need to break the bond, so that means there has to be a certain kind of contact between the reactants, and that contact is something called as collision. Suppose I'll explain you by considering the reactant as car. Just look at this example. See, we have car A, we have car B, right. If I want that these two cars should crash into each other, they should break each other apart, so what is going to happen? Obviously they should collide with each other. Suppose car A is coming with a great speed and even the car B is coming with a great speed, then what happens when they just come closer to each other? They just get crashed, they just get banged with each other, and they just you can say the bonnets or the parts, or you can say they just broke, right. But suppose if I have a car A and we have a car B, car A is on lower speed and even the car B is traveling with the lower speed. So what happens when they are going to crash, when they are going to collide, or you can say when they are going to bang, they will bang, but that kind of the bang will not release in the more breakage, right. It is just a condition of ouch, right. So that means they merely touch each other, but there is not such kind of breakage. So that means for the reaction to happen, keep in mind one thing is very important, that the collision between reactants must occur, right, because we need to, like our first concern is that we need to break the bonds, right, and for breaking the bonds we need to make reactant closer to each other, not closer like just they have to be placed with each other. It's not like that. It is that they should bang with each other with a great force, that that results in the breaking of their previous bonds, and they may result in the formation of some new kind of bonds also. So the formation of new kind of bond is a second concern. Our first concern is the breaking of bond, I told you, right? So that means for breakage, the reactants need to bang with each other with a great force, and when they bang with each other with a great force, they result in the breaking of the bonds. As I told you that we have two cases, car A and car B traveling at higher speed, they just get crash into each other, and they just leads to major loss in the cars, right? But when we talk about car A and B, they are traveling with a lower speed, so when they touch each other, obviously they touch each other, but the loss is not too high. Here we need that loss, right? Because when you are traveling on the roads, you don't want that your car should get trashed or something like that. But here in reaction, what we need that the reactant must crash into each other. They must you can say break each other, and more effective is the breakage, more effective is the collision, more effective is going to be the chemical reaction. Right. So that means we can have two kind of collision. This is clear that we need collision. You know that now, that if we need a chemical reaction to happen, collision is must, right? So this is there is no second thought. Collision is must, because we need to break the bonds, right? Second thing is that we are talking about that not every collision leads to the breaking of bond. As I told you that in this case, two cars were traveling with a greater speed, so they lead to the breakage, more breakage. But when we talk about car A and B, you can say they collide, but the breakage or the bang is not do not occur with a great force. So that means this is a kind of collision in which you can say is an effective collision. This is said to be an effective collision because it leads to the breakage, right? But when we talk about this, they were traveling at very low speed, this is something called as ineffective collision, because it do not leads to the breakage of you can say many bonds. So that means now we are again I am explaining you. The first point is that for the reaction to happen, the collision must take place, right? Because we need to break the bonds, right? Second thing is that not every collision is going to be effective. Not every collision is going to be effective. For the collision to be effective, the reactants should collide with each other with a greater force. Stronger is the force between them, or you can say the more is the speed with which they collide with each other, more is going to the breakage, and more it will lead to the chemical reaction, right? So that means for the reaction to happen, obviously our first point is that collision must take place. Second is that the collision should be effective. Collision should be effective. Now our question is that how we can have these two factors fulfilled, how these two factors will be fulfilled, what should we do to make chemical reaction happen, right? So it is actually that as I told you that not every collision is going to be effective. So that means for the collision to happen, there is a condition required, right? And that condition is that then if we want reactant to collide with each other, they should possess minimum energy, and if they will possess that much energy, then only the collision is going to be effective. Otherwise they could how long they get collide with each other, or how many times they collide with each other, it will not result in a chemical reaction. So that means for the collision to be effective, what is necessary? The minimum energy should be possessed by the reactants, and that energy is called as threshold energy. Right. So I am going to write the word here. So what is that energy? It is threshold energy. So I think it's clear that where this threshold energy is used. Another name for threshold energy is the activation energy, because it is activating reactants. It makes the reactants active, then only they move and they just get banged with each other and just result in the breakage of bond and formation of new bonds, right? So if somebody is going to ask you about threshold energy, how you are going to define it? So write in your copies, the threshold energy is the minimum energy required by the reactants to cause effective collision, so that they can make the reaction happen, or they can make the the formation of products, right? Now I am summing up the points again, so that to make you clear. The first thing I told you that for the reaction to happen, there need to be breaking of bonds, right? Second, I told you for breaking of bonds, there should be a contact, means there should be a collision between them. Third, I told you that not every time every collision will result in the breaking of bond, because some collisions are effective and some collisions are ineffective. Fourth, for the collision to be effected, what I told you, that the reactant should possess minimum energy, then only this collision is going to be effective, otherwise the collision is not going to be effective in any case. And that minimum energy which should be possessed by the reactants to this thing to cause effective collision is something called as threshold energy or as activation energy, because it is simply you can say activating the reactants so that they should break their initial bonds or leads to the formation of new bond, or you can say they should make reaction happen, right. So this is what is the threshold energy. Now when we talk about the units, so as it is a energy, so obviously the unit is going to be in terms of energy, so it is kilojoules per mole. It is kilojoules per mole. So threshold energy is measured in kilojoules per mole. Now I'll explain you this concept more, because this is a very important aspect of chemical reaction, because if this is not possessed by the reactants, the reaction is not going to happen, right. So I'm just going to illustrate you with an example of daily routine. See, suppose I have a ball here, you can see the graph. So what I have in this graph, I have a ball here, do not see this ball at this moment, right. So see, we have this hill, a peak kind of you can say a structure which is resembling a hill, and this is a plane surface. So this ball, let us name it as A. This ball is traveling, and when it travels, it just reaches a point where it cannot travel further, right. The ball is traveling, now it has reached a certain point where it you can say where its motion is hindered. Now the question is that why its motion is hindered. Hindered is because due to the shape of this curve, right, due to the shape of the hill. If it would have not present, then what happened, this ball would have moved in a similar manner and would have reached this point, right. But due to presence of this hindrance, due to presence of this shape of the peak, this ball is you can say facing a difficulty that it cannot move more, right. So it stays here. So this state corresponds to a state of the higher energy. This state corresponds to the state of higher energy because it is at certain height, right. And we know that in terms of potential energy, when height is more, so obviously the energy is going to be more. So that means this ball A, when it is at this point, it possesses the higher energy. We want our ball to move to this point, right. Now consider this ball. This ball is the same ball, not the different one, right. We want our ball to reach this point, and this point is lower than this point, so we say that this corresponds to a state of low energy, right. So that means our ball has to our ball A has to travel from this point to this point, but it is facing somehow hindrance that it cannot travel here. But if like what is the energy difference, if we talk about that, as I told you that this point corresponds to high energy and this point corresponds to lower energy, right. So if what is the energy difference, if we talk about the energy difference, so that means the energy difference is something this, right, because it is at this position and it is at this position. So that means this is something the energy difference. Now as everything in the universe is just seeking the stability, you know that everything in the universe is just seeking the stability, because it moves from the high energy state to the lower energy state just for the sake of attaining the stability, because higher is the energy, less is the stability, less is the energy, more is the stability, and everything in the universe is just struggling for the stability, right. So like in the same way this ball is struggling, right. So this ball wants to move to this point, but it is facing somehow hindrance in crossing this peak, right. But if we just push this ball, right, if we just push this ball with a greater force, then it is going to move and it will reach this point, right. And you know that at this moment when it reaches this point, no more energy from your side is required, because after that it is going to be a spontaneous reaction, and it is just going to fall from the peak to this low position itself. You don't have to supply energy, right. So that means this rolling of ball is a spontaneous reaction, it's clear, right. As I told you that it is at this point, so it is just it will roll down, your initiation is not required. So this is something a spontaneous reaction. But when it is at point this, so it is a spontaneous reaction, the rolling of ball is a spontaneous reaction, but still here it needs certain kind of energy. The energy is needed just because this energy difference between it, because it is at this point and this peak is here, so it needs this extra energy, right. So what you do, you just supply it with extra energy, and when you supply it with extra energy, it gets through this peak, and when it reaches this peak, it is just able to cross this barrier. So we can say this is something as energy barrier. We can call this peak as energy barrier, and this energy which you supply it to our ball A to cross, this is something called as activation energy, because this activation energy just activated the ball, right, so that it can cross this hindrance and can reach to the point where it wants to. That means the point which corresponds to the lower energy state, right. So this is what is threshold energy. I think it's clear. It is simply energy which a reactant must possess in order to you can say remove or you can say again I am telling you, it is just the energy which the reactant must need in order to cross this energy barrier to cause effective collision, so that it can reach to a point of lower energy and higher stability. Now, when we talk in chemistry, if we talk by taking into consideration the chemical view, I have this graph as this graph. Right. So this is just a graph I told you just to illustrate with a daily life example, where I just told you that we have a ball cannot cross this you can say hill due to the shape of the hill, and we need to supply certain kind of energy, then only it reaches the peak, and at the moment when it reaches the peak, as soon as it reaches the peak, no more initiation is required, it is going to roll down itself. That means it is just going to reach the point of lower energy state, and which corresponds to the higher stability. And this energy which you supply it to in order to cross this peak is something called as threshold or activation energy. Now we talk about threshold energy or activation energy in chemical form, right? That means we take into consideration the chemical view. So see this graph we have. So I am plotting graph in with energy on y-axis and reaction progress in x-axis. So what do I get? I get, see, this line corresponds to product, this line corresponds to product, this straight line, right, and this straight line corresponds to reactant. So let us make certain marking in order to just make the clear that what kind of energy difference they possess. So let us make 0, make it 20, make it 30, make it say 150 kilojoules, right. So what do we get to see that like when we talk of, first I am just talking about reactants, right. So this is the graph which corresponds to the reactant, right. So what the reactant already possess this much energy, you haven't supplied energy, this 30 kilojoules, these energies are already possessed by the reactant molecules. So this is something called as ER. Energy possessed by the reactants, they are present, you can say as an internal energy they possess. What energy they possess is 30 kilojoules, right. Now if we want a reaction to happen, if we want our reactant to cross this barrier, if we want our reactant to collide, right, so that means they have to cross this barrier, and for crossing this barrier they need a minimum energy called as threshold energy, then only they can cross this energy barrier and cause effective collisions, right. This graph what we are studying is just to make you understand that what is the threshold energy and how the reaction happen. Again just look at the board. So this 30 kilojoules is the energy which is already possessed by the reactant, right, or you can say it is internal energy which is already possessed by the reactant, or it has this extra energy which it can use for a chemical reaction to happen, right. Now but for the reaction to happen they must collide, right, and it is clear the reactant molecules which are able to cross this barrier, again if the reactant molecules which are able to cross this barrier, they can only cause effective collisions. This is clear that we need effective collisions, we do not need ineffective collisions, right, because effective collisions only lead to the production of product, and we are just looking for products, we are doing everything for the formation of product. So that means this 30 kilojoules is not a sufficient energy, because you can see this peak corresponds to 150. This peak corresponds to 150. So what is the difference of energy between the reactant or you can say this peak energy? It is something 150 minus 130, that is 120 kilojoules, a big difference, right. So that means the reactants need 120 kilojoules more energy if they are if we want them to collide, or if we want to cross this energy barrier in order to cause effective collisions, or if we want to form the products, right. So they need to cross this barrier, right, and for crossing this barrier they need to possess this energy difference, that is 120 kilojoules they should possess. Now, if we supply them with energy, right, so that means if we supply them with energy, then only they are going to cross this energy barrier. And what minimum energy they need? At least they need 120 kilojoules, because this 120 kilojoules, this peak corresponds to the activation energy. That means the minimum energy with which the reactant must possess in order to cause effective collisions, right. So we are not concerned that from where they are taking, we are supplying with electric energy, we are supplying with heating. This doesn't make a difference. The point is that they need energy, right. And if they will not they will not get that energy, obviously the reaction is not going to happen, because they are not going to cross the energy barrier. No collisions, no product, nothing. Right. So that means this difference, you can say, this just indicates the activation energy. So that means in this, activation energy is going to be, if I say it is EC, that is the peak, you can say the energy for the peak. So activation energy is going to be EC minus ER, that is 150 minus 30 comes out to be 120 kilojoules. So in this, 120 kilojoule is an activation energy, that is the minimum energy which the reactant must possess in order to cross the energy barrier, right. And now when we talk about product, you can see that product has lower energy, more stability. So this graph, in this graph, the product line corresponds to 20 kilojoules, right. So that means they possess less energy as compared to reactants. That means they are more stable. Now let us see that what is the difference, this thing. As we know that reactant can happen in both ways. It can form the product, it can also form the reactant. So how we'll come to know that the reaction is going to proceed in a forward manner or the reaction is going to proceed in a backward manner? This is what I am going to explain you now. See, this line corresponds to product, right. And what is the energy of product? That is 20. If we calculate the difference between the EC and EP, this peak and this, now what is going to be the energy difference? Obviously 150 minus 20 comes out to be 130 kilojoules. Right. So that means if I want my reaction to proceed forward, I need an energy of 120 kilojoules, right. And if I want my reaction to proceed in a backward direction, we require an energy of 130 kilojoules. So out of 120 or 130, which is the lesser amount? Obviously it is the 120 kilojoules. That is why the reaction proceeds in a forward manner. Let's see you can say the step which requires the lower energy gets more favored, right. So that means the reaction is going to proceed in a forward manner. That means the reactant is just going to form the product. So this is what I think you got it, that what is the activation energy. So activation energy just corresponds to this peak, that is the minimum energy which is required to cross the energy barrier. And as you can see that the product always possess less energy as compared to reactants. That is why the reaction proceed in a forward manner, not in a backward manner. Now just look at the different other graph.